All right, we are recording. Cool. So let's get started. Today we're doing graphs. Um, the reason why I'm doing this lecture is because Sungjin doesn't like graphs. He's like allergic or something. So you guys are stuck with me. All right. So bit of a forward. Reminder on proof style. So the very first thing you should always do is not to make assumptions. So some of you guys have been pretty good about this sometimes actually, where you'll ask me like, can we assume like, for example, all the integers are either odd or even? And that's a good thing to know. You actually can't assume that. But for the sake of like ease of doing things, sometimes I will allow you to do so. I'll allow you to assume some things like that, but you should ask and you should be very, very careful. Um, okay. Use English effectively. I think most of you guys that are in the course right now are actually doing pretty good on this, but it's actually pretty common if you're like teaching like in the semester to see like kids relying a lot on logical symbols and it gets kind of confusing to read it or just sort of like listing stuff. Um, but good proofs should look like English paragraphs. Like they should flow and then be connected properly. Um, and so at this point in time, I just released solutions to lecture 4. So you should start to get an idea of what proofs should be looking like. Um, and make sure you're reading through all the solutions. Because I think the more you read proofs, the more you can understand how they're supposed to look. The feedback. So one thing about the feedback you get is that the graders will probably not mention something as feedback if you could obtain that information by reading the solution. So definitely make sure to do it. And the last thing is don't write War and Peace. If you don't know, it's a very long book. um, so it takes a lot of effort to write War and Peace, but sometimes you guys end up writing way, way too much. Um, and so what's a good practice is when you think you've gotten the idea for the proof, you think you've basically written it down, uh, take a fresh look at it and try to think, can any of this be reworded to be a little bit more clear, a little bit more concise? Um, and I'm very very gung ho here in this sentence. Every word is necessary. Okay, you don't need to make every word necessary. At least every single sentence should be very necessary. I think that much should definitely be true. Um, but make sure that when you're aiming for concision, you don't cut down on the previous 2 points. Okay. Graphic illustrations and where to find them. There are no illustrations in here. I hate making graphics like that in LaTeX. It's not fun. I'll simply draw for you in a different tab. Oh, I should probably share my entire screen then. Let's do that. I can share the window. All right. Cool. So a graph. So a graph is a very, very fun object. There's a whole field called graph theory, and graph theorists go off and do fun things with graphs. Anyways, so a graph is a pair of two things. The first is called a vertex set. So a vertex set, normally denoted by capital V, is a collection of what we call vertices. And then we have these objects called edges, and edges are just pairs of vertices. So we say that edge A comma B, where A and B are vertices, implies that A is connected to B, or not implies, but rather is equivalent to. We define it that way. All right, so let me just stick a picture in your head real quick if you've never seen a graph before. Here's an example of a graph. Okay. Here's a graph. So what's our vertex set? It's something of size 3. And our edge set is going to be a set of 3 elements where the first one is this comma this, the second one is this comma this, and the last one is this comma this. Okay. Let's see some more examples later. Okay. An undirected graph is a graph, but it has the property that if AD occurs in E, then BA also must occur in E. So is this graph undirected? Well, no, because this appears, but this doesn't. But this graph would be considered undirected. And we can also draw it a little more simply. Just draw this. Okay, so this would be an undirected graph, and so would this. And when we talk about undirected graphs, it would be pretty annoying to talk about AB and BA separately. So we actually consider them to be equal. So if I talk about AB and say something about it, it applies to BA as well. Okay. A self loop is an edge that connects a vertex to itself. So maybe if I throw in this would be a self loop. Okay. So now we have our first big definition, a simple graph. Um, so a lot of people, when they say graph, they mean simple graph, which is kind of annoying. But also other books will straight up just define graph to be our definition of simple graph. So they always have to be a little bit careful. But in general, in Wild, if you see the word graph, they normally mean what we call a simple graph in this course. But while you're in this course, try to stick to these definitions so we can be really clear about what we mean. So a simple graph is an undirected graph with no self loops. So this is not a simple graph. It has a self loop, but this is. And lo and behold, it looks very simple. So good. Okay. Any questions so far? Do you guys understand what is a simple graph? Ooh, okay. Great. Good job, guys. All right, let's continue. Oh, we have examples now. Brilliant. Okay, so the first is the cycle graph. So, as one might anticipate, I really wish I could control Z more, but whatever. Um, here is a cycle graph. Um, here is also a cycle graph. In general, cycle graph with n vertices is denoted as Cn, and these guys are pretty handy for examples and counterexamples both. Okay. What else do we have? The connected graph. Okay. So well, this would be C3, and let me just convert this over here to to K4. So the connected graph on n vertices, written as Kn, in this case K4, because we have 4 vertices, is where every pair of vertices is connected. So your edge set is kind of maxed out while still remaining a simple graph. And I'm realizing now that everywhere that I've written graph in here, I should have written simple graph. Oh no. Okay, well, I think you guys see the issue. It's too easy. It's too easy to forget. I'm sorry. You can't blame me. Um, we'll just continue. I'll pretend that didn't happen. Okay. Let me draw you the path graph. Path graph is kind of what it sounds like. It's just a path. So you have n vertices kind of connected in a row. This would be P4. And the last one is a star graph. I actually didn't know about the star graph for a while, but it is pretty handy in some weird circumstances. So the star graph is I always forget if it's off by one in what way. Okay, so Sn has n leaves. So the star graph on n actually has n plus 1 vertices. So like S3 would have 3 things coming out of it like this. So this is a star graph with 3 leaves, or S3. Okay. And this one is actually called a claw. I guess because like it looks like a claw. I don't know, dude. But yeah, this one has some important meaning in graph theory. Okay. So yeah, these are just some examples of like fundamental graphs that can kind of come up as examples somewhat frequently. But there are obviously like huge families of graphs that exist. But these are fairly standard. Okay. Okay, a path. Love these things. Okay. So it's a sequence of unique vertices. So remember, it has to be unique. So you can't sort of loop back on yourself. Such that each pair of consecutive vertices are connected. So what do I mean by that? So for example, here is a path in the cycle graph. If this was 1, 2, and 3, then the sequence 1, 2, 3 would be a path. Okay, because 1 is connected to 2 and 2 is connected to 3. I also could have done 2, 1, 3 or 3, 1, 2 or like literally any triple of these vertices because they're all connected. And the same here. Literally any subset of the vertices in a connected graph will form a path because they're all connected. And you can put them in, you could put that subset in any order. There's two paths of length 4 in here. We say a path has a certain length. If it's just the length of the sequence, this path has length 3. And there are 3 paths of length 3 in here, I think. Probably. Okay. A cycle is just another path, but the last vertex needs to be connected to the first. So as Michael pointed out, if your graph was directed, then actually it should say V and U should be connected. So why is that? Well, let's say I have a path, right? In just a regular graph, which will have edges. Well, if I had this is not a cycle, but now this is a cycle. See? So it should be connected in this direction. So I'll probably, let's just like fix this lecture like for next year. Just maybe I'll just give like some primordial graph, and then a simple graph will just become like, I'll just call it graph, and then everything else will be fine. That's probably the right way to do this. Yeah, my bad. Okay. A graph which is free of cycles is called acyclic. So let's look at the graphs we have. This one is not acyclic. Surprisingly, the cyclic graph is not acyclic. The connected graph is not acyclic in general, but K2 and K1 are acyclic. These guys are acyclic because you don't have enough vertices to form a cycle. Oh, and I guess there's actually a flaw in this cycle definition. We don't consider a cycle of length 2 to be a cycle unless we're in like a graph instead of an undirected graph. So what I mean by that is like, if we have an undirected graph where we would just write edges like this, then this is not considered a cycle. But if we're in a regular graph, which has directed edges, then this is considered a cycle. This terminology is getting really terrible, isn't it now? I'm sorry, guys. Thankfully, in your proofs, you can just make it clear what you mean, so it's not really a huge deal. Yeah, go ahead.
In the example you just gave with the directed graph, is it like that's a subset of a larger graph? Like there would be other.
Yeah, there could be, yeah, but like I mean specifically, like, this is 1 and 2. Like there could be other crap going on here, right? But I'm just saying like 1, 2 would be considered a cycle. Sorry.
But aren't they the same graphs, or is it like the first graph could potentially have been undirected? I mean, sorry, like directed.
It's not like this is not a very precise thing I'm saying. Like it's just what we consider.
Okay.
Yeah. Also, you'll probably never have to think about this detail.
Very good.
Yeah, so don't worry about it. Alrighty, Roof. Let's continue. Yeah, I'm sorry. This is a huge mess. Whatever. A graph is connected. For any two vertices, there's a path between them. So you haven't actually seen any graphs which are not connected. So let me give you an example. So let's say my graph has 3 vertices, and I just have one edge like this. So this is not connected because there's no way to go from this vertex to this vertex using a sequence of vertices that have edges between consecutive vertices. But everything else we've seen, literally everything else is connected. And now our first really good definition is a tree. So a tree is a connected acyclic graph. And I should have written simple graph here. I'm really, really hating myself right now. Okay. A tree is a connected acyclic simple graph. Okay. So let's take a look at some examples of trees. So this is not a tree because it has a cycle. This is not a tree because it has a cycle. This is a tree. Why? It's connected and it's acyclic. This is a tree as well. It's connected and acyclic. It's not a tree. This is not a tree either. This is not connected, but it is acyclic. Okay. So in general, trees might look something like this. You're maybe used to this computer science. But this is just like a nice way to draw a tree. They don't always have to look like this. So maybe you, it's not immediately clear to some people if something's a tree or not. But the check is obviously first check if it's connected and then check if there's any cycles. Okay. All right. We're very close to doing a proof. Just 2 more definitions. Oh, okay. So if it's undirected, so I guess now we have to think about this detail. So if a graph is undirected, we don't consider cycles of length 2.
Oh.
I'm sorry. I'm so sorry.
No, I was just thinking because like if we have like even a linked list of size 3, wouldn't you have a cycle going one way and then back?
Oh my
Or do we
god.
consider it one edge?
Well, no, because that wouldn't be a path because you can't repeat the middle vertex. Remember, paths are sequences of
Oh.
unique vertices. So
Yeah, okay.
if anyone's confused what happened, Michael's saying, well, why wouldn't this be a cycle? Well, I would go 1, 2, 3, and then I can't go anywhere now because 3 is only connected to 2, but we've already visited 2. Okay.
Okay, yeah, thank you.
Yep. Good question. All right. Where the hell was I? Degree. Okay. The degree of vertex is just the number of neighbors it has. And in particular, if a vertex has degree 1, it's called a leaf. So let's just look at something. This guy's a leaf. This guy's a leaf. This guy's a leaf. This one's not a leaf. It's not connected to anything. Leaf, 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 leaf. Both leaves. All leaves here. And 2 more leaves. Okay. I understand what a leaf is now. Okay. This one's tricky. Well ordering principle. I call it WOP for short. So every non-empty set of positive integers contains a least element. So what we mean by least element is just it has a minimum. So it has some x, such that x is in the set, and it's less than or equal to everything inside the set. Okay. So the idea, very briefly, is well, okay. Let's imagine my integers, right? So I have my positive integers. So let's say zeros here. So I have some subset of everything that appears out here, and WOP says, okay, somewhere along here is a minimum for this set. So if your set had like, if your set was like this guy, and maybe some other things later on, it has an element, and we can just call it x. Okay. So this may seem obvious, right? Because like, you may think to yourself, well, if I just lay out my set, I can just look at the smallest guy, and surely it should be there somewhere. But you do have to kind of you do have to state it properly. And WAP is actually pretty important. We will use it shortly. And there's also a reverse direction where you can say, for example, let's say we have a subset of naturals, right? So start from 1 and go onwards. If there's an upper bound, then a non-empty subset will have a maximum. So like, let's say there was just any upper bound, then we know that it has a maximum and maybe it's like here or something. So it works in the reverse direction as well. All right. All right. So there's also something called the well ordering theorem. So I think somebody mentioned this in their homework, and they said like assume that we can order this set. So we can say like a1 comma dot 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 an. So well ordering principle allows you to order finite sets. Why? Because basically, you can always pick a smallest element at any point in time, and then you can sort of set that aside, and then you pick the next smallest, and then so on and so forth, right? So you can just order it by doing that. But actually, you can well order any set, which is very interesting. And this is equivalent to something known as the axiom of choice, which we mentioned before. So you can do math assuming choice, and you can also do math not assuming choice. And this is pretty interesting. And okay, I think Sangjin must have added something to refer to this later, so you have that to look forward to. Okay. All right, first thing we're gonna prove: every tree has at least 2 leaves. So let's build a little bit of intuition here. So let's look at P2. P2 just looks like this, and look at that, we have 2 leaves. Okay. Let's look at this tree. We have lots of leaves here. That's great. We have 5 leaves. Okay, so why do we always have at least 2 leaves? Well, maybe I can reason like this. Uh, if I didn't have any leaves, that means that everything is connected to like 2 things. And that seems a little sketchy because if I kind of started at some vertex and I kept going and I never ended anywhere, that would kind of imply I'm going to run into myself again at some point. It kind of seem to imply I have a cycle. But trees are acyclic. So I can think, okay, well, that means I have to run into a leaf one way if I started here, but I can also go another way, or maybe I'm a leaf myself. So if this guy is a leaf, then I'm done. But if he's not, then I have some other way I can keep running the other way. And now I kind of found 2 leaves, right? So here, that's the intuition for why I should find 2 leaves in any tree. So now let's actually do it formally. But I won't drag you through this. I'll just sketch it out. Um, the idea is this. Let's take a set S. Well, okay, let's first take a graph G equal to VE, where G is a tree. G is a tree. Okay. So now let's take S as a set of path lengths in G. Did I spell length correct? I didn't. I have the muscle memory for writing it correctly, but I don't know how to actually spell it. Anyways, so we can actually use WAP here. So WAP implies that since S is a subset of positive integers, we have at least, sorry. Okay, we're actually gonna use WAP backwards here. My bad. So S is bounded above. So why is S bounded above? Well, because the longest path can be at most V in size. And V is finite. We only discuss finite graphs. So everything in S is bounded above by the cardinality of V. So WAP implies that there's a maximum path length. So let's call this just M. Okay? Is max path length. Okay. So that means that we have some path that looks like V1 VM. So my claim now is that in this longest path, which is, well, it's not necessarily unique, so maybe I shouldn't say the longest path, but in one of the longest paths, my claim is that the start and end must be leaves. So let's consider why. So we can arbitrarily let S be a neighbor of V1, right? So let's say S is connected to so we actually want to show that S is just equal to V2. So how do we do this? Well, if S wasn't V2, right? Let's say S just connects off here, then we would actually just have a longer path, right? We would now have a path of length m plus 1. But we still need to be careful, because what if this S was actually just some other vertex somewhere down the line? Well, if S was equal to some Vi for I greater than or equal to 2, and the problem we have is that, well, actually, we would have a cycle, right? Have a cycle. We could get there one way by going through V2 all the way down, or we could jump right to it. That would be a cycle. So S can't be V3 or afterwards, and it can only be V2 basically, because we have to make sure that we have no cycles. Okay. So that means that V1 only has one neighbor, which is V2. That means it's a leaf. And we can also argue pretty much the same exact way that VM is also a leaf. So there we go, we found 2 leaves. Okay. Does that make sense? Cool. You can let me know if I'm going too fast. I can revisit a detail if you need me to. No? Okay, everyone's good? Continue on. All right, every tree with n vertices has n minus 1 edges. So let's get a little bit of intuition here. So let's look at one of my trees over here. So if you notice, if I sort of root my tree, if you're a computer scientist, you'll be familiar with this. If I root it, I kind of put it at the top here, right? I notice that every vertex in here kind of like has a parent, right? Along the path to the root. So like this guy's parent is the next vertex along the way to the root. So every vertex has one edge above it, connecting it to its parent, except for the root itself. So you can kind of see I'm getting my n minus 1 by doing that. And now, if I were to make a cut in this graph, right? If I deleted this edge, well, now I'm not connected, right? I have fewer than n minus 1 vertices, or sorry, edges, and I'm not connected. If I were to add an edge instead, now I have n edges. Now I have a cycle. And now things are very strange. Okay, so there's kind of this intuition that if you have too many edges, you become connected, or sorry, you end up with a cycle. If you have too few, end up disconnected. However, just because you have fewer than n minus 1 edges doesn't mean that you don't have any cycles. Because, for example, maybe your graph is just really stupid, right? There's all these like random vertices, and then I just have these three that are just kind of chilling in a cycle. So I have fewer than n minus 1 edges, but I still have a cycle too, despite not having n or more edges. Okay. All right. So yeah, this one goes by induction. All right. So this proof is actually a really good example of how to make a mistake. Uh, why is V bounded above by cardinal? So it's not V that's bounded, it's S that's bounded. Is that what you meant? Okay, so remember, so S was the set of path lengths, right? So every path uh, is a sequence of unique vertices. So you can't have more than cardinality V vertices that are unique. So S has to be bounded above. Okay. All right. Where was I? Induction. So I'll actually show you how to do this induction incorrectly. All right. So let's start with the base case. The base case will be correct. I'll just tell you that. So what we're trying to do is we're trying to show P of n is true for all n. Now let's define it. Set a tree with n vertices. Vertices implies minus 1 edges. Okay, sorry for my bad handwriting. Okay, so the base case is very simple. P1 is true because if we have one vertex, we have 0 edges and life is okay. All right, so now let's do Pn. And this will be incorrect. So, well, sorry, I mean Pn implies Pn plus 1. So here's how I can do it incorrectly. Please spot the error. So I will say, okay, let G be a tree with n vertices. So okay, you imagine your tree. Oh well, let's not do that. Okay, you have your tree with n vertices. And now I say, okay, let's make it a tree with n plus 1 vertices. How can I do it? Well, okay, pick a vertex. Pick any vertex. I sound like a magician. Pick any card, right? And just tack on this vertex. So now here's my proof that this is a tree with n plus 1 vertices, and this proof will be correct. So what have I done here? So I need to make sure that I haven't introduced any cycles, and that my graph is connected. So let's talk about connectedness first, because that's a little bit easier. So connectedness is the property that for any two vertices u and v, there's a path between them. So let's say the u and v both come from here, the original tree. Well, that's okay, right? Because that original tree was already connected. So the path should still exist the very same. The edge set is only a superset now of what it used to be. Now, if one of those vertices is this vertex, well, notice that it's connected to this guy. So if u was here, for example, and v was out here, well, this was connected to v. So now my path from u to v is simply go from u to here and then use the path you had from before. So we're connected. And now assume that we've introduced a cycle somehow. Well, if the cycle started at some vertex u and ended at some vertex v, and both of them were inside here, that's not possible because this was already acyclic to begin with. And, well, okay, I need to be slightly more precise. If it started and ended inside of here, the only way for it to be a cycle is to somehow include this vertex. But it's only connected to one thing, which means that a path can only end here. It cannot come here and come out. And so that actually does both parts of both cases, where my starter ending is both in here, or maybe one of them is out here, because you're only connected to one thing, so you can't have induced any cycle. Okay, sorry, that was a little sloppy, but I think it's pretty intuitively clear. So if you want to make it rigorous, it's not too hard. So by adding this one vertex, we maintained connectivity, and we didn't introduce any cycles. So now I show that I have n plus 1 vertices, and I have n edges. So my claim is that I've implied Pn to mean Pn plus 1. So what did I do wrong? So I started with a graph with n vertices, and I know it has the property, it has n minus 1 edges. And I ended with a graph with n plus 1 vertices and n edges. What's wrong? This becomes a lot easier once you try to convert the statements to the underlying logic. And I think actually last year, some people, I think multiple people made this mistake. I'll give you a minute to think about it because it's pretty important. Let's see here. So my question is, did I prove Pn plus 1 by assuming Pn? Well, the answer is no. Oh, why? Because to prove a for all statement, I need to universally instantiate. How did I construct the graph, this G? I started with the graph that has n vertices. I did not arbitrarily instantiate a graph that has n plus 1 vertices. I didn't do that, so it's not a valid proof. It's close, and it has the right idea, but it's really not a proof. So how do I fix it? How do I fix this proof? Well, it's not too hard. First, I universally instantiate this graph G. So I say it's a tree, and it has n plus 1 vertices. And now I have to make use of Pn somehow. Now I can start thinking about Pn once I've done that. So what can I do? Well, I know this. Every tree has at least 2 leaves. So that's great. I pick one leaf and I cut it off. Now I've sort of done the reverse of what I did in the fake proof, right? I start with something bigger and I cut something off. Because I can't be sure that I can construct for a smaller object a bigger object, right? It's not necessarily clear to me that I can do that. But to start from the bigger object that I universally instantiate and cut down to a smaller thing that I know something about, now I can talk. So now the proof is mostly the same, right? So I start with n plus 1 vertices, I pick a leaf, and now I ignore it. And I say, okay, this thing ought to be a tree. How do I argue that? It's very similar to what I argued before. And so that smaller graph, right, that has n minus 1 edges. Now simply, I remember, oh, this is vertex, this leaf that I cut off before. That gives me one more edge and one more vertex. And similar to what I argued before, that's still a tree. Well, okay, I don't even need to argue it's still a tree because I assume it's a tree. I assume that the big graph is a tree, so I don't need to think about that anymore. Okay. Does it make sense why what I did initially is not a proof? I think I've lost everybody. Oh no. Okay. Let me see if I can construct a similar example. No, it's not quite so easy. Oh, okay. Yeah, here is an example where actually the proof is wrong. Okay, so let's do that. So let's say for all s subset eq n. So let's just mean this to be natural numbers. I know it's sloppy notation, but whatever. Um, S has n elements. Implies that all of S is either. So that's a scary statement, right? So you already know it's false, right?
Oh, I only see
Go ahead.
the Teams to meet. I don't know if you're sharing something else.
Oh my god, I'm gonna shoot myself.
Uh-oh.
I thought I was sharing my screen. I was sharing the window. This is really sad. Hang on. This is really sad. Because I wrote out like the logic that probably should have helped. And I can't undo in Notepad. Anyway, so I was trying to write this, but so this should have helped you. Okay, so let me just speak about this very quickly. So there's a for all here in Pn plus 1. And the point is to prove this, I need to universally instantiate. There's no other way around it, right? And I need to assume this about what I've instantiated. But anyways, let me do this. Let me do this other proof now. And thank you for letting me know that you can't see this. So this implies that all of S is even. Okay. And let's say let's just use this, whatever. Pretty much the same. This one element implies all of S is even. So the fake proof would be that okay. I pick a set S of n elements, and I know all of it's even. Now I take the maximum element and I add 2 to it, right? So let S subset EQN such that n, then all of n. Now let prime equal x as and all right, so here's my fake proof. And now this one definitely doesn't work, right? Because I use pn to construct something, and then I just did I just showed like this, but it did not universally instantiate. So it's much the same what I did with my graph. Um, so I need to make sure that whenever I see a for all, right, and even in the back of my head, right, because I didn't write for all, right, in my proof, but it's in the back of my head. I need to make sure that I universally instantiate properly. Okay. Is at least this clear to everybody? Why this fake proof is doing strange things? Okay, some more sense, just a little bit more. You remember Adam sort? What about it?
Oh, the first instinct I have with Atom sort is you can
Oh
sort the
yeah,
first n elements, and the
yeah,
final one gets sorted in. But then it
yeah,
doesn't work because you can sort anyway.
yeah. So if you guys read the problem about Adam sort, which I didn't name by the way, Sanjin named that. um, a fake proof might look like, okay, well, you can sort the first n guys in this many steps, and then you sort the last guy in n steps because there's only n times it can move backwards or something like that. Um, and that doesn't work because actually when you have the bigger object, right, suddenly the statement about the smaller object doesn't even mean anything anymore, right? A subarray is not what the algorithm's acting on, right? So there's many instances where this mistake kind of easy to make, but you can always be sure to avoid it by universally instantiating properly, basically. Okay. Hopefully that makes some more sense. I think actually for next time I'll probably directly include this in the notes so you guys can see it ahead of time. Okay. Let's continue though. I think hopefully at the very least it's clear that every tree with n vertices should have n plus one edges. Or say n minus one edges. Okay. All right, last definition, bipartite graph. So I'll draw one for you. Okay. So bipartite graph is basically god damn it. Should be simple graph. No. everywhere that mistake is. Okay. It's a simple graph where I can sort of partition the vertices and something nice happens. So all the vertices on this side and all the vertices on this side um, are such that all the edges go over this dotted line. So it's a very informal definition, I know. But this would be a bipartite graph. Maybe this guy's feeling lonely. Let's give him another edge. Okay. So this is a bipartite graph. Why? Because there's no edge that connects two vertices on the same side. It's not allowed. Okay. So formally, let's define what we mean by partition of the vertex set. So there should be two A and B, two sets A and B, such that their union is the entire vertex set, and their intersection is empty. And now the edge set, we can actually describe it as just being a subset of A Cartesian product B, right? Because we couldn't have any edge which is in A Cartesian product A because that would go from A to A, and likewise we cannot go from B to B. Okay, so that is a bipartite graph. This kind of graph shows up a lot in computer science. So for example, what we could have here is we can have clients making a request. Okay, hello, we want to download some information, or we want to upload some information, and we need to do some processing on it. And we have servers distributed across the world. We need to figure out how to handle these requests. Who should get which requests? These edges means that this client could possibly connect to this server. Now, how do we make sure how to connect these guys to maybe we want to minimize the server load? We don't want to put too much burden on one server, something like that. So there's a lot of variations of problems on this, of variations of problems, yeah, on this. So it's fun to think about it. And also there's like Hall's marriage theorem. You can look that up. It's like, okay, these are boys and these are girls, and obviously no boy would like another boy. That is completely preposterous, back in the 1800 when they wrote this. And okay, so how do we make sure that like everybody is like happy or something like that? It's silly stuff. Okay. Let's consider some graphs and see if they're bipartite or not. Um, so okay, let's think about C3. Can somebody tell me, is this graph bipartite? So C3 is not bipartite. So if we want to prove that, it's a little bit annoying, right? Because in order to show it's not bipartite, so to remember what's going on here, well, we say there exist two sets A and B. So we need to show for all A and B, such that blah, 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 we don't have the edge set as a subset here. So I'll save you the pain from having to think about that. Let's close these, we don't need them anymore. So what will happen? Let's say arbitrarily, without loss of generality, that this guy is an A. So why can't we say without loss of generality, and what does that mean? Well, it's saying that whether this guy is in A or B, it doesn't matter. Because if this guy was instead in B, then we'll just swap A and B. So it doesn't really matter which one it's in, we'll just arbitrarily call it A. And we didn't lose generality. What I mean by generality is precisely what we get from universal instantiation. Okay. So without loss of generality, because we could just swap A and B, we can say that this guy should be an A. And now we have a problem. So this guy can't be an A. It's not possible. Otherwise, we have an edge from A to A. So this guy ought to be in B. Now we have a real problem. Where should this guy go? It can't be an A, because then this edge is from A to A. And it can't be in B either, because this edge would be from B to B. So we have nowhere to put this guy. And so there's no way to do bipartite partitioning here. Okay? Does that make sense? Okay. I only have one person in my lecture right now. Only one person wants to talk to me. If it doesn't make sense, feel free to say so. Tripartite. Yes. So I think we talked about coloring in the homework. Yeah. So in question 5.5, we talk about coloring, and since we have some time, I can just discuss it a little bit right now. So we can assign colors to vertices. So we can have a function f, which takes in a vertex and gives us a color, which is just numbers because we don't have much imagination here. So we'll say a vertex is colored 1 or something like that. And coloring, proper coloring, is one where two neighboring vertices do not have the same color. So maybe you were in social studies in 6th grade, and they give you a map of the world, and like here is like America or something. I don't really know how to draw a country. Don't say anything, please. And here's like Mexico, and you're like, okay, well these guys got to be different colors if they're next to each other. So you go ahead and you color this. You get your number 1 colored pencil and then your number 2 colored pencil, and you're really happy. So you might be familiar with something known as the 4 colors theorem. It says that any map that you draw like on a regular like 2D plane, you can with 4 colors make sure that no two adjacent bodies have the same color. And maybe you try to figure this out, and you grab like a few colored pencils, and maybe you realize like, oh, I need like 6 or 7. So it turns out it's actually kind of hard to ensure this, and the proof of the 4 color theorem is really insane. Let me remind myself. false disproofs. Yeah, that's funny stuff. Yeah. It was done by computer, and I'm trying to remember how many cases there were. 400 pages. Yeah. For the four color theorem, and let me show you pictures since I'm sure they have a nice picture. Here we've colored this map with four colors. Um, it's it's very hairy. And nobody really even accepted the proof because, well, if somebody just gives you 400 pages of computation, you're not really going to be pleased with it. And I think to top it off, they were wrong at the beginning, and they had to go back and fix stuff later on. So this has a very sad history as a theorem, but it's considered to be proven now. So yeah, there's some history for you. Okay. But let's get back to business. Tripartite. So let's say three colorable. And this graph is of course three colorable because we can color this one, color this two, and color this three, and we're done. No two vertices even have the same color, so the edges literally don't matter. Okay. Is there anything more to be said here? Yeah, actually, I will talk a little bit more. So notice that being bipartite is the same as being two colorable, which you have to prove it, but I'll take it for granted right now. But so what about C4? Is C4 two colorable? Is it possible to assign colors to these vertices such that no two adjacent vertices have the same color? Well, the answer is yes. Um, and simply just go around here like this. So now more generally, can someone try to give me an if and only if? Cn is two colorable. Colorable. If and only if what? So C3 wasn't. We saw that. C4 we could. Someone generalize this? Yeah, has to be even. Um, and I don't want to spoil anything. I think yeah, I don't think this should spoil anything. Oh wait, no, it does. That's precisely problem 4. Okay. So I guess I won't say anything further. You guys can think about that, but that should help with the 4 a little bit. Okay. Are there any other connected graphs other than? What do you mean? So, uh, oh wait, did I say connected graph earlier? I meant complete. I might have said connected by accident. Um, definition 510. So it says there's a path between them, not necessarily an edge. So let me just correct myself just in case I said the wrong thing before. Kn is the complete graph on n vertices, and it's complete because uh, E is basically just equal to V squared minus self loops. Just really bad notation, but um, but wow, really, my bad. That should say complete. Where is this? Oh wow, yeah, okay. My bad. That should say complete. I think I also sometimes mix it up myself, so that's not really surprising it's in there. Okay, my bad. Question 1 is very sus. Oh yeah, 514 is I'm actually surprised I was able to fool everyone because I came very close to the issue. Um if you guys want to discuss it right now, go ahead. Why is it not true that every tree should have at least 2 leaves? What did I say here? Yeah, you can and should yeah, exactly. You have trees with one vertex, so how can you possibly have 2 leaves? So n equals 1 graph, you could just say C1, P1, K1. Not S1 though. That would be S1 is equal to P2. If you're not sure what I mean, S1 is a star graph with one thing sticking out of it, but that's the same thing as the path graph with 2 vertices. But this graph is the same as P1. It's the same as a complete graph with 1 vertex. It's the same as cycle graph with 1 vertex. You can't do that because your vertex set must be finite. In our definition up here, V is an arbitrary finite set. Um, so, but let's say we consider infinite graphs for half a second. If V was the integers, and we connect 2 vertices if they differ by exactly 1, then what am I trying to say here? You would be connected, you would be acyclic, but you would not have 2 leaves. So the statement wouldn't be true for like infinite graphs in general. Um, there's something to be said here, but we'll talk more about relations next lecture. But what I'm trying to say is that graphs are not that different from relations. Okay. Any other questions? Uh, no. No. It says it has a minimum, and you can use it backwards. So think about it like this: positive integers are basically bounded below, and that's why they ought to have a minimum. But they're not necessarily bounded above, right? So let's say I'm talking about positive integers. So I could just take the entire set of naturals, right? So the entire set of naturals doesn't have a maximum, right? So it's constantly increasing upwards. So WAP doesn't say that. It says basically if you have either an upper or lower bound on a subset of integers, then correspondingly, if you have an upper bound, you have a maximum. If you have a lower bound, you have a minimum. You could also have both, and that implies both. The reason why WAP is only stated in one direction, like for positive integers, you have a minimum, is because you can actually use that to prove the other direction. If you want to prove it, it's good to think about it too. Okay, anything else? No? Okay, good. All right, thank you guys for coming. Have fun with the homework. Bye bye.